Thank you, Dana. And hello, everyone. The work that I'll be describing was performed by myself and my colleagues for the Renewable Resources Planning Act assessment that the Forest Service conducts on a periodic basis. The RPA, Renewable Resources Planning Act, requires the Forest Service to look into the future and project future supply and demand conditions for the major renewable natural resources across the U.S. So I'll be showing you some results of recent work along those lines. My talk won't be specific to urban areas or urban forests, but certainly has implications for them. I'll be covering 3 topics. The first being projections of climatic and water supply conditions across the U.S. And when I say the U.S., I mean the 48 states. Hawaii and Alaska are not included because of data limitations for what we were trying to accomplish. The first slide here shows projections from global climate models of temperature on the left and precip on the right. This is average conditions across the U.S. We used 7 different climate models, each run at 2 different future emissions levels. Those emissions levels are called RCP 4.5 and RCP 8.5. And the 4.5 and the 8.5 are just forcing levels that are possible in the future. The 4.5 level is a rather optimistic future where emissions peak in 2060, although greenhouse gas concentrations continue to grow, but at a lesser rate throughout the rest of the century. The 8.5 level is more a business as usual future with emissions continuing to grow throughout the century and then certainly greenhouse gas concentrations continuing to grow. And on the left side, you see the temperature projections for those 14 different cases, 7 climate models by 2 different emissions levels. And the heavy lines, the heavy black and heavy red, show the average for the 2 emissions levels, 4.5 and 8.5, across the 7 models in each case. And the story here, as I'm sure you're well aware of, is that all the models are projecting increasing temperatures throughout the century. The increases are greater for the higher greenhouse gas concentration level, and there's a fair amount of difference among the model projections, especially as we get further into the future. So a fair amount of uncertainty about what's going to happen in terms of the specific level, but no uncertainty about the direction of the change. Between now and 2080, if you just look at the 2 averages, U.S. average temperatures are projected to increase by 3.6 degrees Fahrenheit. The graph shows centigrade, but so the increase would be about 2 degrees centigrade or 3.6 Fahrenheit in the optimistic case. And in the business as usual case, the increase in temperature is over 4 degrees centigrade and 7.5 degrees Fahrenheit, so a lot of change. So now looking at precipitation, The models, again, are sort of all over the place, and they are from the near future on throughout the century. So a lot of disagreement about average precipitation levels. But I should say a lot of disagreement across the specific models, but the averages are quite similar, and basically they're showing a slight increase in precip over the century. That increase is the result of the higher temperatures, which causes greater evaporation, mostly off the oceans, and that moisture in the air ends up as precipitation. I guess we're all aware of this possibility given the recent hurricanes that we've all been hearing about. So more of that is expected in the future. So we've got increasing temperatures and also increasing precip in general. And now on the left you see the result of those two changes, plus other changes like wind speed that I'm not showing you. And here we see the difference, precip minus natural evapotranspiration, ends up as water yield. That's water in the stream or water ending up in the groundwater aquifer, and thus available for diversion and use in cities and elsewhere. And here, again, there's a lot of disagreement across the models. And if you look at the averages, the heavy lines, across from now into the future, a slight decrease. So just to move along, we'll now look how these changes are arranged spatially across the U.S. The two maps are for the 4.5 and 8.5 forcing levels. So the optimistic picture on the left shows the temperature rise from from the beginning of the century to 2060. And the rises are greater in the northern part of the country than they are in the south. On the right side, you see the less optimistic future. Same picture in the sense that the rises in temperature are greater at the northern latitudes in general, but the changes are higher everywhere, given the 8.5 than they are the 4.5. Here are the changes in precipitation between 2000 and 2060 across the U.S. You see that the increases, that generally increasing precipitation is not projected to occur everywhere. In the southern and partially middle Great Plains, parts of the Southwest, and California, plus some isolated locations elsewhere, such as Florida, are expected to receive less precipitation as we go into the future. And there are more areas receiving less precipitation. This is the red area at the higher greenhouse gas concentration level, the less optimistic future. Putting those together and looking at changes in water yield, we see that most of the U.S. is projected to receive less water yield, available water, after the natural effects of evapotranspiration off the landscape. Less water available, except the larger Northwest, where the increases in precipitation are sufficient given the expected changes in temperature to result in more available water. So that's sort of the background climatic and water yield changes as we understand them. A lot of uncertainty about the specifics, but general agreement about the larger trends. So what does this mean for water shortages? We did a large modeling study at the monthly time step, and our spatial unit of modeling was the 4-digit HUC. It's a watershed. We had 204 of them. They covered the 48 states. So we're modeling water yield and water demand in these basins into the future, and counting when a basin's water supply is or is not sufficient to meet the projected demand. And in this modeling, we keep track of reservoir storage, abilities to transfer water from one basin to the next in canals and pipelines and tunnels under the mountains. And so, just to give you the whole list, water yield is in a given basin in a given month is equal to the I should say the water supply in that basin is equal to the yield that occurs in that basin. That's precipitation minus evapotranspiration, plus inflow from upstream basins, plus net trans-basin diversion into the basin, plus reservoir storage that was left in the reservoirs in the previous month, minus an in-stream flow requirement, and minus required releases to downstream basins. And you can see the maps of reservoir storage capacities and basin interconnections there at the bottom. So the result of that, averaging across the 7 climate models in each of the 2 cases, the 4.5 and the 8.5, we see that, this is changed in the man, excuse me. Pardon me, I wasn't going to get into this, and I'm going to skip it and move on to the results, just in the interest of time. So the frequency of monthly shortage in the mid-future period, that's centered around 2060, are as shown in these 2 maps of those 204 basins in each case for the RPC 4.5 and 8.5. And you see the water shortages are concentrated in the greater Southwest and California, plus a few areas elsewhere. The top ones are showing you the average across the 7 climate models, and then these other maps I've just added show the minimum and maximum projected levels of shortage. So again, this gives you an idea of the uncertainty about the future, which is largely the result of our uncertainty about precipitation and temperature in specific locations at specific times in the future. Finally, I will tell you a little bit about how the water is being used, and specifically how much is used for irrigation. In situations in the future where there are water shortages, something needs to be done about it. It has to be addressed in some way, and there are various ways to do that. Using less water, water conservation is, of course, one. There are opportunities for technological advances that would help that. But another one is shifts in water use across water use sectors. And so in that light, it's interesting to see how much water is being used and by what sector. This graph shows trends in total water withdrawal. That's the height of these columns. And it's divided up into consumptive use, the red, and return flow, the water that goes back into the stream. That's the blue part. And you can see that both total withdrawals and consumption peaked in about 2000 and has been dropping slightly since then, despite the continued increase in population. Now we're going to take a specific look at 2010 water consumption and see how much of that water goes to which sector. And as the pie chart shows, 81% of water consumption across the U.S. goes for agricultural irrigation. Just 7% for domestic and public use. Not 7%, it's about 8%. Those numbers aren't percents. And about 6% for industrial and commercial use. This shows the percent that goes to agricultural irrigation by basin. And you can see there's quite a difference between the west and the eastern part of the U.S. The graph at the bottom here shows for the east and west the cumulative percent of water across the eastern basins and western basins going to agriculture. And you can see as from the text there that in the east, half of the eastern basins use less than 23% of their water for agricultural irrigation, whereas in the west, half use over 90% of their water for ag irrigation. Now, some of that agricultural irrigation is really critical to our food supply, and is going to be needed in that purpose into the future. But a lot of the irrigation in agriculture is used for less critical crops, specifically feed grains and forage crops. I'm talking about feed corn, alfalfa, sorghum, and such crops, where there is some leeway, some ability for change. Finally, this graph shows for each of the 204 basins the amount of water going for irrigation, but it shows not only the amount for agriculture, the blue part, which I've been talking about up to this point in the two previous slides, but it adds on to it the amount of water going for landscape irrigation in the basins. And as you can see, in most basins, much more water is used for agriculture than for landscape maintenance, although that is not the case with all of the basins. There are a few where landscape irrigation is a substantial percentage. Just to wrap up, precipitation is expected to decrease in roughly a third of the U.S., and water yield is expected to decrease in roughly 3/4 of the U.S. Future water shortages are most likely in the central and southern Great Plains, Southwest, and California. The vulnerability increases typically are caused by a combination of decreasing water yield and increasing water demand, much uncertainty remains about the specific levels. And for the U.S. as a whole, 81% of total water consumption currently goes for agriculture and another 4% for landscape irrigation. And future changes in these relative shares are likely. Thank you. There's a list of publications that'll be available later if anyone is interested in pursuing any of these topics further. So thank you very much.